Good morning, chemistry students. Here are your Chapter 15 Day 2 notes. We're going to be starting on your outline. It's not written on your outline, but at the formation of cations and finishing through halide ions, which is the end of Chapter 15, Section 1. So the formation of cations, this is not written on your outline. However, it should go wherever you ended your octet rule stuff. And before electron configurations for anions, there's quite a bit of information here. So I would start right underneath wherever you ended your octet rule notes. So we talked about the octet rule, right? And the octet rule states that in forming compounds, atoms tend to achieve the electron configuration of a noble gas. An octet is having a set of 8 valence electrons. So specifically, we have 8 electrons in our highest occupied energy level, and we have the electron configuration ns2np6. We talked about the fact that the atoms of the metals tend to lose valence electrons, leaving a complete octet in the next lowest energy level, and the metals tend to form cations. The atoms of the nonmetals tend to gain electrons or share electrons with another nonmetal to achieve an octet. So we're going to kind of specifically focus now for a little bit on what happens when we form cations. So remember, as we get started here, we're talking about a neutral atom to start with. And what makes an atom neutral is because the number of protons equals the number of electrons. So, a positively charged ion which we call a cation or a cation, I'll always call it a cation, okay, is produced when an atom loses one or more valence electrons. For metals, typically, again, it's going to be your metals that form cations. The cation name, so to name this when it becomes an ion, is equal to the metal name plus the word ion. So we have to somehow differentiate it from just being a neutral atom. So we add the word ion to the name of the metal. Metals and their cations have many chemical differences. What I mean by that is a neutral metal atom and the cation that it forms, they do not react the same way chemically. Okay, they act different chemically. So we're going to take a look at the group 1A cations. For example, we're talking about sodium, which has an electron configuration of 1s2, 2s2, 2p6, 3s1. And so that sodium atom is going to lose an electron and it's going to become a sodium ion. which has an electron configuration of 1s2, 2s2, 2p6, which, remember, is the same as neon. So what that means is, okay, a sodium ion, which is its name, right? Because we take the name of the element of the metal and we add the word ion. Sodium ion has 8 valence electrons in its what we call valence shell. Right? So in sodium as a neutral atom, its valence shell is the 3rd energy level, and it just has 1 electron in it. But when it undergoes ionization and becomes an ion, now its highest occupied energy level is the 2nd energy level, and it has 8 electrons in it. Another way that we can look at this is we can look at it by looking at our electron dot structure. So we can say sodium, which has 1 dot because it has 1 electron in its valence shell. It loses its electron because it undergoes ionization. And now it's a sodium, and we don't show any dots around it because that 3rd energy level now doesn't contain any electrons. And we have an electron left over. So what happens in our group 2A cations? They are going to lose 2 valence electrons to become a noble gas because they have 2 valence electrons. So its choices would be it could lose 2 or gain 6. It's going to be easier to lose those 2 valence electrons. So to look at this one as an example using that electron dot structure, if we look at magnesium, which has 2 valence electrons because it's in group 2A, it's going to undergo ionization and lose 2 electrons. And we're left with magnesium with a +2 charge, no electrons drawn because, again, it's lost those electrons in that valence shell, and it has 2 extra electrons left over. So, again, our tall columns are representative elements on the periodic table. Our number of valence electrons is equal to our group number on our periodic table. Group 1A has 1, Group 2A has 2, Group 3A has 3, Group 4A has 4, Group 5A has 5, Group 6A has 6, Group 7A has 7, Group 8A has 8 valence electrons. Now, it's not as nice of a pattern. There really isn't a pattern when we talk about our transition metals. And so again here, remember, we're talking about groups 3 through 12, or we also called them our group B because their group numbers are followed by a B. These are the short columns of the periodic table. For the transition metal cations, the charges of the cations may vary. And some of them do not get a noble gas electron configuration. Therefore, they are exceptions to the octet rule. They oftentimes, though, do get a pseudo. Pseudo, remember, means like a fake. They get a pseudo noble gas configuration. Often, so their N equals whatever D has 18 valence electrons. And because of this, the charges of the transition metals cannot be predicted. You're going to get a helper sheet that you will get to use on tests and quizzes. It's posted in Google Classroom as a helper sheet, okay, that will tell you the charges of the transition metal cations. So the electron configurations for the anions. Again, kind of a review of what we've talked about before. We've already talked about what an anion is. An anion is an atom or a group of atoms with a negative charge. An anion is produced when an atom gains one or more valence electrons. Unlike cations, the name of an anion is not the same as the name of the nonmetal. Remember, it's mostly nonmetals that tend to form anions. The name of an anion usually ends in "ide." The atoms of the non-metallic elements attain their noble gas electron configurations more easily by gaining electrons than by losing them, because the atoms have relatively full valence shells. So again, anion, atom, group of atoms with a negative charge. We produce an anion when an atom gains one or more valence electrons. Unlike the metals, where to name a cation, you just take the metal name and add the word ion. It is not that simple with an anion, okay? But names of anions typically are going to end in "ide." And the atoms of the nonmetallic atoms attain these noble gas electron configurations more easily by gaining electrons than losing them, because they already have quite a few electrons in their valence shells, or their highest occupied energy level. So to take a look at this, we're going to look at chlorine. Its electron configuration is, it has 17 electrons, so it's 1s2, 2s2, 2p6, 3s2, 3p5. Chlorine is going to get an electron and become a chlorine ion, whose electron configuration is now 1s2, 2s2, 2p6, 3s2, 3p6, which is the same as argon. We can also look at this using that electron dot structure. So we can say chlorine is in group 7A, so it has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. Again, it doesn't really matter that much where you put them. It's going to gain an electron and become chlorine with a negative charge. And so it's now going to have 8 electrons, 3, 4, 5, 6, 7, 8. So there's our electron dot structure for chlorine when it becomes a negatively 1 charged ion. So chlorine and the other ions that do this are called halide ions. These are the ions produced when atoms of chlorine and the other halogens, which are that's the special name for the elements in group 7A, gain electrons. All of the halide ions have 7 valence electrons, so they gain 1 electron to get the electron, or to get the noble gas electron configuration. All right, to look at then like one final example, we're going to look at an oxygen atom, which has 6 valence electrons because it's in group 6A. So remember, oxygen's choices are it could lose those 6 valence electrons to become like helium, or it can gain 2 valence electrons to become like neon. It's going to do whatever's less, so it's going to gain those 2 valence electrons. So it gains 2 electrons and becomes oxygen with a negative 2 charge and 1, 2, 3, 4, 5, 6, 7, 8 electrons. So your homework tonight is number 12 on page 418, questions 1 through 6. Have a good day. Talk to you tomorrow.